Greetings, everybody, and good evening. Welcome, welcome scientists and citizens of this great, big, weird, wild, and wonderful world in which we live. Welcome and thank you for joining us for yet another Guelph Physics live stream. I, as always, am your humble science communicator, the Great Orbax, and thank you for spending your, I suppose, Tuesday evening with us tonight here. We're here, located, yes, in Physics Hollywood at the University of Guelph. And as part of our ongoing series, tonight's an interesting one. We actually have a fun opportunity tonight to get to chat with three former Guelph Physics alumni who have now all gone off to actually work at the same place, a company called Xanadu out of Toronto, Ontario, Canada. So without any further ado, I guess we might as well bring them in. Let's get a giant live stream round of applause to Paul Finlay, Rafal Janik, and Tim Leisti. Hello. How are you doing tonight?
Great, thanks.
Good to see everybody. I'm glad that Rafal was able to join us. I know it was tight getting you in here at the last minute, but we managed to get everybody in and on board. So here we're gathered here tonight with this basic idea that we're going to get into the idea of quantum computing. You all work for a company called Xanadu, which I believe has the universal mission of bringing affordable and usable quantum computers to everyone. Is that correct?
I don't think you ever said affordable. You never said affordable.
Yeah, if you're close. Useful and available to people everywhere.
Well, that's an important decision to make, I suppose. But I guess, you know, one of the things we wanted to do was to talk initially and try to get people's motivations and get a way to sort of set the groundwork for what we're going to talk about tonight over the course of the next hour. And so I wanted to pose a question to the three of you and get you maybe to answer one at a time. On my screen, we've got Paul here first, so I'll start with him. And just ask you right off the spot, what's the most exciting thing about the world of quantum computing?
The most exciting thing for me, I would say it's the potential for new drug discovery. So one of the aspects of quantum computing that I think is going to be really transformational as we develop quantum computers is going to be in drug discovery. I mean, we're all kind of living through right now a time when being able to really quickly develop things like vaccines, new drugs is really important. And that's one capability of quantum computing that I think is going to be really exciting to look forward to, for sure.
Interesting. So not unlike Huey Lewis, you want a new drug, and quantum computing is going to bring that on. How's that for a timely reference for the kids out there? Huey Lewis and the Noobs. Rafal, I'm asking you the same question. What's the most exciting thing to you about the world of quantum computing right now?
Yeah, for me, it's the cure for depression. And the reason I say that is like we're really up against a wall in terms of Moore's law computationally wise. We're generating more data than ever. We're creating crazy models for dealing with that data. The computational workloads that people are throwing at it, even from a physics side, is really drastically pushing not only the computing power, but also energy demand through the roof. You know, the AWS data center consumes like a single one, and I'm thinking of one in on the East Coast, just outside of DC, has the same kind of energy footprint as the city of Toronto. So it's not a small amount. And we've had so much progress in the last 50 years that was really driven heavily by the availability of kind of this ever increasing, exponentially expanding computational power. And from a fundamental level, like we're hitting the limit of scaling classical compute. You already see that individual processors aren't getting much faster. What we're doing now is just horizontally scaling them. And quantum computing is really the cure for that. Not only, like Paul said, will it enable phenomenal use cases like drug discovery, what I'm more excited about is kind of the ubiquity. You know, maybe not in the next 20 years, but in the next 50, having quantum computers be co-processors in kind of all devices. And the really cool thing about a quantum computer is it's a classical Turing machine as well. So everything that a classical computer can do, in theory, a quantum computer can do as well. So you can even see a world where all computers will eventually be replaced by quantum computers. Whether that'll happen in our lifetime, we'll see. But that's the part for me that's really exciting.
Well, it's I've been just rolling through my brain here trying to pull a Huey Lewis in the News reference for anything of what you just said, but unfortunately I couldn't get anything. Sometimes jokes are funny if you just explain what the premise would have been. Tim, same question to you. What's the most exciting thing about quantum computing to you right now?
Yeah, to me, it's the potential for a massively disruptive technology. I mean, there's, as Raf said, there's so many problems that we're just throwing huge amounts of computational power at right now that by looking at them a different way, i.e. with a quantum system as opposed to a classical system, we have the opportunity to have far simpler novel solutions for those problems that we can get far more rapidly. Even, to take as academic an example as the amount of computational power it takes to simulate a system from first principles. So from basic computational level, from quantum mechanical equations. That's a massive undertaking on a classical computer, but on a quantum computer, you're dealing with a quantum computer simulating a quantum system. That's potentially a very easy problem to solve now. So the understanding that we can get out of these systems and look at much more complicated systems to grow our understanding in those areas is potentially huge.
Tim wasted his youth writing C and Fortran code for first principle gold nanoparticle simulation. So this is a particular pain for him.
Yeah, I'm speaking from past trauma. Yeah.
Now, I guess, so we've got all this exciting, all these exciting ideas and this groundbreaking achievements that quantum computing will potentially bring us. But I guess we've overlooked probably the most basic part of what a discussion of quantum computing should involve, which is a definition of what quantum computing is compared to classical computing. A lot of our viewers are undergrads or people currently doing the graduate work, but there's probably a lot of people watching who are completely it's outside of their wheelhouse, even what the definition of a quantum computer is. So does one of you want to try to give us perhaps a layman's definition of the difference between a quantum computer and a classical computer?
All right, I'm going to pick this one up. I was going to throw it to Paul, but he seems not responded to the question. So there's any number of ways people like to kind of tackle this. One of the classic ways people like to describe it is this idea that superposition affords you the ability to explore all the paths at once. I personally don't like that explanation a lot, just because it kind of ignores the fact that when you go to read out the system, you still have to read it out classically and pick the correct answer. So the way I'd like to think about it is you have these two fundamental quantum principles of superposition and entanglement that you're able to exploit in building this quantum computer. And what they do is they make the computational complexity of simulating that system incredibly difficult, meaning that if you actually wanted to solve it with a classical computer, it would either take you a computer that you can't, physically create with kind of all the resources in the universe, or that if you had the resources we have today, it would take you till the heat death of the universe to run that computation. So it's completely inaccessible. And then the real goal becomes, how do you take the problem you really care about and map it onto the system? So you know that the system can perform this operation that is computationally very complex, and now you actually need to map it onto that. Kind of the magic that happened in the 90s is that people came up with a formalism. So how do you actually take arbitrary problems and start mapping them onto quantum computers? And this was done with this, approach of gate-based universal quantum computing. So how do you break it down in kind of atomic parts of computation that then you could build up into larger algorithms? So I'd say quantum computing exploits superposition and entanglement in order to increase the computational complexity of what you could do. And it's not running faster. It's not running massively parallel. It's doing a completely different computation to get at the same problem. There's a nice video, I think, from a British university. I can't remember off the top of my head which one it is, but it demonstrates finding the solution as a car driving through a city. And then the quantum computer is just an airplane that takes off from one airport and goes to the other, taking the shortcut. And I like that analogy quite a lot. It doesn't speak to the physics at all, but it gives you a sense that it's something very different that allows you to bypass the classical computation.
So my takeaway is that quantum computing is faster, that it can model these much more complex systems, But I mean, physically, what are you doing? What is it? I've been doing some reading, watching. Well, I mean, I say I've been doing some reading, but what I've actually been doing is watching videos about quantum computing. The idea of your sort of binary idea of off and on that takes place in a classical computer that's just done with a gate. In a quantum computer, you're doing that by probing this idea of entanglement. Is that right?
Yeah. So normally what you would do is you'd there's a number of modalities that you can do this on, and kind of maybe one classic one people are familiar with are nuclear magnetic resonance, and spin was kind of the first example. Yeah. People now use trapped ions that are laser cooled that can interact with each other. But the idea is that you're able to prepare a quantum state on a single qubit. So you can think of this as the spin of an atom, the current in a superconducting loop, or in our case, an optical state of light. And you're able to control that with very, very fine control to prepare it in a certain state of superposition. So control that probability distribution. And then what you're able to do is apply a series of gates where they're there to change that probability distribution, or whether it's to take two of these qubits and interact them with each other in some way. And based on these basic building blocks, and there's only a number of gates that you require to have the full universal set, you're able to kind of build up and develop these quantum algorithms.
Interesting. So I guess that's the basic difference between the two, is now that you're generating this binary code out of examining these states and the changes that are taking place within them. It's so, I mean, before we get too deep in the weeds in terms of what a quantum computer is and quantum computing, let's talk a little bit about the fact that all three of you are graduates of the University of Guelph and of Guelph Physics, and you all separately went off on different paths before all kind of coming together in this company, some of which I've been informed by Tim even as recently as 3 months ago. So do you want to give a little, we get a lot of our viewers who are undergraduates who, especially now as we're getting closer and closer to exams, are trying to potentially having a bit of a harder time seeing life after physics. Does anybody want to share their story as to how they went from undergrad and eventually ended up here, 15 years later?
Yeah, sure. I'll start with that one. So for me, went through actually quite far. I mean, I did my undergrad at Guelph. I did a master's and PhD all at Guelph. I loved being there, and I loved the environment at Guelph. The professors in the physics department are fantastic. Learned a lot there. Really enjoyed physics. So I continued on to do a postdoc. I actually went to CERN at the LHC, doing low energy nuclear physics, but at the LHC. Which was a great place to be. Felt like a rock star at that lab, which is a little bit surreal. And then, approaching the end of my postdocs, I had to make a choice really if I wanted to continue on in academia. And really, going past the postdoc stage, you'll often hear people say that the postdoc is sort of that last point in an academic's life where they're really free to do research without responsibility. You're not necessarily writing grant proposals or supervising students or teaching. You're just doing research. You're doing hands-on work, and it's fantastic. And I can totally speak to that because it was great. And so I decided, do I want to keep going down this route and start doing less and less hands-on, things in terms of like analyzing data, solving problems, or do I want to do that? And so, this new sort of newish field of machine learning, data science, AI was really exploding at that time. So I got turned on to that and realized, I'd never been calling it machine learning, but data analysis as part of experimental physics is machine learning. This is something I knew very well, and I really enjoyed that aspect of what I had been doing with physics. So I found that transition pretty natural. I ended up working for Royal Bank here in Toronto as a data scientist, which was really cool because a bank, it's a big company, but they have a ton of different types of data. So I got exposed to all sorts of different types of data and data analysis and modeling, machine learning and AI. That was really cool. So I did that for a few years, but I'd been talking with the guys at Xanadu for a little bit since I knew about this company. Another Guelph grad, Nathan Kiloran, he's had a PhD in quantum computing, and has been at Xanadu, and I'd been talking with him, and they were looking to expand into working on machine learning and AI products. This is something that I had been doing, and so I've been talking with them about their plans along those lines, and thought this would be a great fit. It'd be really exciting to go work, in quantum computing, building something that is really going to help, sort of change lives and change the world, which is super exciting. And that was in 2019, and I've been there almost 2 years now. And I got to say, even though at a startup, you're going to be doing a lot of different things, which is great for someone like me who likes doing a lot of different things. And having that background, going through experimental physics, having all that exposure to, writing and maintaining code, and being able to self-manage projects and prioritize work, and all of these kind of things are skills maybe you don't realize you're picking up as you go through undergrad and grad school, but they're invaluable when you get into the working world, especially in tech. And I mean, ever since I've been having a great time at Xanadu. There's no shortage of work at a place like Xanadu, especially for people with our kind of background. I think that's kind of why, I'll let the other guys chip in on how they feel about this. But I think this is why we've kind of all coalesced here, because there's that certain mixture of skill sets that really work well at a company like this. Having that technical background, that knowledge of physics, and that understanding, but also being able to take on different things, like being able to code, being able to develop software and understanding how software works and what its role is in building products or services or supporting what we're doing. Having that broad view that you get by doing, like an advanced degree, I think is pretty important. We have a lot of MSc and PhD people at Xanadu, and not all in quantum physics either.
Well, it's an interesting route that you've kind of taken, and this idea that doing nuclear physics, that working for a bank managing data, that now going on to machine learning and artificial intelligence for a company that's making quantum computers, seem like incredibly different requirements for a skill set. But so you're saying that there's a huge overlap across all three.
Yeah, fundamentally that overlap, being really curious, liking to solve problems, and being a critical thinker, which is, I think, in my opinion, one of the things that you really develop as a physics student, right? And going through physics, that is one of the most important skill sets that I've found is often missing from people not from those kind of backgrounds. And it's really important when you're pursuing technologies that we don't even know if this is going to work out. And I mean, having that mentality, right, of like exploring new things, trying new things, not being sure, and willing to take on and learn all the time. I mean, always learning new skills, new things is critical to this. And I think that's where that kind of, maybe that Venn diagram intersection lands.
Well, I was always fed when I was doing my undergraduate in the late 90s that a physics degree was a degree to learn how to learn. And it seems like you're actually proving that right somehow, that you're able to sort of drop somebody with a physics undergraduate or graduate degree into any sort of situation, and they can bring a different sort of insight, or this idea of somebody with critical thinking skills to sort of offer solutions to problems. I want to play devil's advocate here, and I want to get a definition of what you think machine learning is. You had said you had mentioned, and I don't see that seems remarkably confrontational when it's not intended to be that way at all. You were saying that machine learning is basically the same stuff that you were doing with the nuclear stuff that you were doing with RBC that now you're doing at Xanadu. What is this all-encompassing definition of machine learning that takes all that into account?
Oh boy, I mean, Raf and I have talked about this quite a bit. I mean, technically, if you look at the definition of artificial intelligence, it's a for loop is artificial intelligence. So really, this definition, what is machine learning? I mean, really, it's the way that it's described, learning parameters of a model. So, for example, taking data, having a parameterized model, then training on that data to learn the parameters of that model. So, for example, linear regression is machine learning. I mean, fitting a straight line to data, that's machine learning, because the weights that fit this line are learned from the data. That's really what we mean by machine learning. It's the same as there are obviously extensions to this, but the fundamental maybe high level concept to sum it up is you're using data to inform a model that is parameterized.
Mm-hmm. Neat. Yeah, I mean, I think that it's kind of interesting that somebody with an undergraduate degree might be sitting there right now working on a lab, and that they're effectively doing machine learning, and they aren't even realizing it. Tim, we've kind of left you in the dust here. Tell us a little bit about your story of coming from Guelph, what you sort of did, and how you ended up at Xanadu.
Sure. I mean, long story short, it's all Raf's fault, but I'll go into the details now. So yeah, I did my undergrad in theoretical physics at the University of Guelph, mostly because I just didn't like labs, so I decided to do more math instead. And then I was, most of the way through my master's, and sort of life happened and decided I should probably start making a real income. So I sort of made the decision to switch out of academia, finished up my master's, headed off to an advertising agency out of Burlington. So the way that happened is, I just sent out resumes looking for software development jobs, because it was sort of always a hobby of mine, and I was able to hone my skills through my master's in doing that. Ended up connecting with a CTO of a company who was a bit of a science geek. Most of the interview ended up being Feynman questions, the style of how many grapefruits fit in a school bus, that type of thing, where you're basically just testing your thinking abilities, your problem-solving skills. So that position had absolutely nothing to do with science. But as Paul said, I think the foundation of what you learn as a student in physics really suited that position well. There was a lot of problem solving, a lot of critical thinking. I ended up doing a lot of troubleshooting for client side issues. I was there for a while, and then ended up picking up an opportunity at a large healthcare company. So that was a completely different experience. Now people's lives were literally dependent on what I was doing. I wasn't a doctor or anything, but I was providing the information that the doctors need to do their jobs. So that, again, having that background of being able to troubleshoot and being able to problem solve, that was a key asset in that position. So it's still just software development, which you don't learn as part of a physics education. It's something that you sort of have to pick up on your own. But even being self-taught, having that background and foundation of knowledge really sort of gave me a leg up in that field, I feel like. Moved on to another position. Eventually, Raf, out of the blue, connected with me on LinkedIn. Networking is great for everyone. And basically said that he was trying to take over Xanadu with Guelph alumni, and would I be interested? And it was honestly an opportunity I couldn't turn down. The chance to sort of get back in the game after a decade out of science, and even to just be tangentially involved in something as disruptive and interesting as quantum computing, I couldn't turn it down.
Well, how intimidating is it to walk away from, to not be involved in like a hardcore science group for about a decade, and then to come back surrounded by people who have never left?
It's pretty intimidating, I'm not going to lie. I sort of am at the level of, I still kind of remember what an eigenvalue is, but beyond that, my quantum mechanics is basically all gone.
I guess Wikipedia is a best friend in those opportunities where it's like, I understand all this stuff, but maybe you should explain it to everybody else in the room, just so that they are all up to speed.
I read the titles of articles that I get shared amongst our company Slack, and that's about as far as I go. Yeah.
But in all honesty, I mean, did you find that you were able to retain a lot of that stuff? I mean, clearly you kept up with your skills because you were doing similar work in different environments, but were you able to retain any of it, or was there a bit of a sharp learning curve coming back into it?
The general concepts are all there. I certainly couldn't dive right into the math involved in any of it, and some of the hardcore algorithms, I'm not involved in that side at all. And I don't expect I will be unless I do some serious research back into that realm. But the general concepts of what we're doing and why it's exciting are definitely still there. And I think that's an important part of why I'm here, is I recognize just how important what it is that we're doing is for the advancement of this technology.
Exciting. And I guess that just leaves you, Raf. What do you want to talk about your journey?
Yeah, first I'm going to say that Paul and Tim are lying completely. nothing that they said is the truth. So I'll try to correct some of those things that they said incorrectly. But
Perfect.
yeah, Tim and I actually went through the same year at Guelph, so we did our undergrad and our masters at the same time. So I'm going to say fundamentally, I was never a great student.
Agreed.
I don't think I ever had you as a TA, but we could bring Chris Schultz-Nielsen in to attest on my academic prowess.
He usually pops in partway through. I think he's in a lab right now, but he'll be in the chat room at some point. Don't worry.
Yeah, I actually.
Besides that, speaking about the chat room, we do have a live chat going here on both Facebook and YouTube. If you do have questions about quantum computing or about a future in physics and continuing on, please feel free to post them, and we'll get to them as we can. I'll toss it back to you, Raf.
Yeah, I was going to say, if Chris does come back on, I do have some questions about my advanced physics labs and the marking that you did there. But I actually, through the advanced or the senior project that we had, I ended up working with Vladimir Ladozhansky, who at the time was a fairly young faculty and looking for students kind of anywhere he could get them. And that landed me a master's position at the University of Guelph, which was great. Again, also computationally focused, writing kind of simulations and then doing some of the experimental side. When I left, I really had no expectation of staying in academia or physics at all. I ended up working at a research hospital at Sunnybrook, doing MRI research, mainly focused on neurodegenerative diseases and a little bit of cancer as well. Oddly, in a group full of physics alumni as well from the University of Guelph. I've just followed them along everywhere I've gone. I did that for a little bit. NMR and MRI are fairly closely related, so it was a natural jump. And actually started my PhD at the University of Toronto in the field of medical biophysics. I think I had forgotten how much, let's say, that type of research. I love research, but the being a graduate student didn't agree with me. So shortly after beginning, I actually chose to leave and focus on starting my own efforts, my own company, to provide consulting services around computer vision and ML systems for medical and industrial applications. Did that for a little bit, ended up working at a few really large companies doing a very similar role, so building out machine learning teams. In fact, I think on 3 separate occasions, I tried to hire Paul prior to us both working at Xanadu. So when he was leaving his postdoc, and then I believe twice more while he was at RBC. But through all this, there's actually a group of us. So Nathan, who couldn't make it today, but he's also a physics alum from University of Guelph. Myself, Paul, and a couple other people used to have these dinners on a monthly basis, where we'd all actually go out and complain about how much we hate our jobs. So Paul was at RBC, I was at a large multinational, Nathan was working actually for the Vexter Institute at the time. And one day he came and he said, there's this crazy photonics quantum computing startup. I think I'm going to take the job. And I think Paul and I spent the entire dinner trying to convince him not to do it. He had an offer from Xanadu and an offer from Element AI at the same time for a substantially more attractive offer. So we thought he was crazy, completely crazy. A year and a half went by, and I think Paul and I both got fed up. And at the same time, we both started. I think Paul actually suggested I also start talking to the people at Xanadu. And after like a couple of months worth of discussions, I made the decision I was going to come across and join Xanadu. But basically told Paul that it was like a murder-suicide pact. I'm going if Paul's going, but if he's not going, I'm not going to join either. So finally, my plan to work with Paul came to fruition. So we both started, I think, a week apart. I started a week before Paul. Yeah. Originally, both with the idea of building out the kind of classical machine learning capabilities within Xanadu in order to support some of the quantum computing efforts. But quickly, our paths diverged. So I ended up being more customer-facing, now heading up the product efforts. Paul stayed on more of the technical side, kind of pushing the classical ML pieces, and then now also contributing mainly to our cloud effort, where Tim is also putting the majority of his effort towards. The thing maybe that I have less rosy colored glasses on for is what out of my kind of past education really served me well. And for me, it's really that kind of, I don't know how to phrase this properly, punishment that a physics education gives you of never knowing whether you're actually correct or not. So I don't know if everyone else has had this experience, but definitely anytime anything worked in the lab or with your code, you knew you were wrong. Like fundamentally, the reason you thought it was working was because you made a mistake. And if you're transitioning, especially to machine learning, where the tools are so easy to use, the data is so abundant that it's actually really easy to build a model that tricks you into thinking that you're doing a good job. That having that, I'm not going to say negative, but just that real
skepticism.
That understanding of the scientific process and saying like, just because I have a accuracy of 98% on this model, is it actually doing what I think it's doing? And 90% of the time, it's no. You've made a terrible mistake. So that has served me the most, and it's actually now being in a position where I've been hiring a lot of people in the machine learning space over the last decade. The number one thing I see in terms of a difference of people coming with a machine learning background versus like a hard scientific background, whether it be physics or biology or chemistry, is this massive difference in that when they build a model, they'll immediately come up and say, great, we're done. It does exactly what it's supposed to do. But there'll be some underlying assumption that is just horribly wrong that breaks the whole thing. Whereas with the physics grads, they'll always say, it's not working, it's not working, it's not working. And then you just have to be like, okay, it's good enough. Trust me. Like we can get it out the door. We can ship this.
There's this unending quest for perfection.
Yeah. Or the other dichotomy you see where someone with a machine learning background jumps straight to the fanciest algorithm they can think of to try to solve a problem, whereas the STEM person says, okay, what's the problem we're trying to solve? What's a baseline? What's a simple thing I can do? Start from there, get it right, and build on it, which is really the fundamentally right approach.
Totally. I mean, it's one of those things that having become a physics educator from being a physics student, I always thought it was so cool to see all the big demos or these big explanations. But when you come down to it, sometimes the most simple setups are the most exquisite, where there's no other room for error and you're just probing one individual thing. There's a couple things that you've touched on that I kind of wanted to get into. And Rafal, we'll go with you right now. Coming from a physics background, it seems like you're doing a lot of work in management. And how have you found that transition from going from science to managing people and to hiring even, or running groups or starting your own business? How is that for you?
Maybe I should say I also never met a physicist that didn't think they could do anything. So, so I think that goes a long way too. I think it's it just even in my academic role at Sunnybrook, having been there for a little bit before becoming a student, part of what kind of discouraged me from continuing on was this added responsibility of training students, leading grant efforts and things like this. So originally I thought that I would never like this and I would be completely an individual contributor for the rest of my life, just working on the technical pieces. I love that part. I still try to do it every so often. I probably haven't written a line of code in close to a year now, which is maybe a little bit sad. But I also love just the variability and kind of seeing the whole picture. And I'm not sure whether that's just a personality issue that I have, that I maybe need to have control over a whole bunch of things, or whether it's something that was developed with the physics curricula. But I definitely would say that doing a STEM undergrad or even graduate school in no way diminishes your ability to pick up those skills later on. It does take effort. It does take time to, it's a completely different skill set. But I find that it complements a STEM education really, really well.
Well, and that tie. I mean, it's shocking in these live streams. We somehow just fold into these elegant segues continuously, because that ties in nicely to this question that we've gotten. We got a question from Facebook. Actually, no, this is from YouTube. Adam says that they're a first-year undergrad at Guelph, and they were wondering if you had any advice for getting your foot in the door in a STEM field. We'll go through the grouping.
I was going to say, I have lots to say always, so I'm trying to give Paul and Tim a chance to speak.
Well, I mean, we've got three people who have taken three similar but very different sort of approaches to end up at a career at the same company. Does anybody want to speak to what opportunities undergraduates should try to avail themselves of so that they can move towards getting work?
It's a good question. I don't know what I mean, for sure, take advantage of, any internship opportunities, summer student opportunities to do work. That's great, right? Expose yourself to that early. Other than that, I mean, first year, I always think like you got time, but that's an old man comment for me.
I know myself, I spent a couple summers working within the physics department, which I think was really helpful because you get a much broader, I wouldn't say education, but just sort of sense of working with other people and just other tasks that you wouldn't normally do as a student. So I think that's really helpful, is just getting that exposure to the rest of the world outside of your first year classes.
I was just going to say STEM is such a broad field, right? In terms of all the possible directions you can go in. So I'd say if they're thinking of more an academic side, definitely those opportunities within the department, within the university to do research while getting paid for it during the summer, were just fantastic. Like I think all three of us ended up doing most of our summers working within the department at the University of Guelph. That being said, what I would say is probably really, really crucial now more than ever is to get those software skills up. Any opportunity you get in order to, and I'm going to say not only learn how to code, but like learn proper software development practices. So whether it be version control, whether it be how do you actually plan and manage a project, like all these little things just make you completely invaluable, not only to employers, but also to scientific groups. Like you can really transform what happens within an academic group if you can come in and show them what real version control looks like.
Well, it's interesting. We've heard this mirrored by several sets of guests in the past to the live stream where it's one of the biggest pieces of advice is that if they could go back to their younger selves and say, learn how to code, learn Python, learn something, so at least you can have that to bring to the table. You're coming from probably a fairly skewed viewpoint where coding's quite a bit important with machine learning and quantum computing. But I mean, you hear it across from people who have taken on all different types of disciplines within physics. I also think it's an interesting thing that you mentioned about taking on positions within the department. I remember as an undergraduate, I was all right as an academic, never top in the class, but well, I mean, we went to school with Dr. Massa, so it was difficult to be top in the class. But within I was head and shoulders above him, but I mean that was mostly just physically. But the thing would be that even doing your undergraduate, it's difficult to know if you want to stay in academia or if you want to work in a physics lab, and getting those opportunities to work with people. And see, are you an experimentalist? Are you a theorist? Do you want to build things? Do you want to do coding? Do you want to learn about stuff? I was lucky enough to get to work with the Dutcher group where I got to sort of be part of every level of an experiment and recognize that that's what I really enjoyed, was being involved in every level of building, coming up with an idea, building an experiment, creating a model, doing it, and trying to fit that stuff afterwards. So, it's good to get those skills up to get a career in STEM and to get a career in physics, but it's also important to see if you even actually want to continue a career in that direction, or you want to take it somewhere else, like Paul and his pawn shop there.
Yeah, getting that very
going to the pawn shop. Not going to make any money. Yeah.
that varied experience, at least for me, was really important. Like I spent a summer working in a lab building a vacuum chamber, another summer literally making handcrafted geometric models. Another one just running multiple choice tests through a computer. And all of those give you a different side of the world that you're stepping into as an undergraduate student, right? So it's very important. You see all those different facets.
You see all these different elements to it, which you kind of like, I don't know, naively, I think when you're, again, this is, as Paul was saying, old man reflections here. But it's like when you're younger, you kind of see this like, oh, this is what a scientist is. But it's not until you actually start to work in the field to realize that there's all levels to it, and everybody has different sort of, everyone has different skill sets of things that they want to pursue. And I mean, some of them are applicable to certain sciences, some of them aren't. So it's getting out there and trying to figure out what you really want to do beyond just studying. Now, to that end, speaking of things that you want to do, Raf, you had mentioned this before. I know this is a project that the three of you are very deeply involved in, is this idea of this cloud project and making this quantum computing accessible to people who can use your quantum computers online. Do you want to talk a little bit about that project from Xanadu?
Yeah, I mean, we launched our first quantum computer, so a qubit device, completely photonic.
Okay, so we're going to have to go through the parts of it. Talk about these photonics. I watched a video about it. Sorry, I mean, I read a book today about can you give sort of the elevator pitch of the photonic chips?
Yeah, so I mean, there's kind of two things. The first one is hardware that we call NISQ hardware. So there's near-term intermediate scale quantum devices or noisy intermediate scale quantum devices. And really what we're talking about is kind of the quantum computers that are available from us, from people like IBM, Rigetti. Now even on AWS, you can find 2 different devices available from their partners. And these are really great devices for experimenting with, for starting to develop algorithms with, but they don't deliver on that full promise of quantum computing. And really what you need is fault tolerance and universality. So fault tolerance just means that every time you program a qubit, every time you make an operation with a qubit, there's a chance that the environment will interact with it and destroy that information. And you need to correct for that. Or else the moment you take a couple steps, even if you're at 99% like fidelity, after 20 steps, you'll just have garbage. So this fault tolerance is the big kind of next step. And you need lots and lots of qubits in order to kind of distill a good quality, or what we call a logical qubit, out of this. So you go from about, let's say, 1,000 or 100,000 to 1. Right now, if you look at IBM, I think they're sitting in the 50s. Google's is at 53 qubits. We're sitting at 40. And the real question is, how do you take it to that next step? And what really is awesome about photonics is that that path is kind of clear. You need a couple things. You need to be able to manufacture these things. And the really cool thing about using a photonic substrate is that you use very standard CMOS manufacturing processes, the same stuff that builds the microchips and the devices that we're using right now. Whereas the other approaches are really unique in terms of materials. The next one that you need is really an ability to network these devices together. And by network, I don't mean classically. I mean, you want to be able to entangle qubits on one chip with qubits on another chip. And this has really only been demonstrated optically so far. So even if you're doing trapped ion or superconducting qubit-based approaches, you're going to want to be doing it optically. And that's really hard to do with high fidelity. Luckily, we already demonstrated that kind of with the first chips that we pushed. So now we're really in this phase with the photonic approach, which is about scaling this up really aggressively from the 40 qubits we're at right now to 1 million qubits, which is about where you'll really be able to start solving these really big problems Paul was talking about of, drug discovery, developing new catalysts, simulating quantum systems we can't simulate today. The other really great thing about photonics is it's all the computation happens at room temperature. So normally with a quantum system, you have to super cool it down to, millikelvin or lower. And that's mainly because a quantum system really just wants to interact with anything around it and destroy that qubit. The great thing about photonics is light in general doesn't care about most of the stuff that's around it. Our biggest source of losses or noise is just loss. The photon bumps into something and gets absorbed.
So this is the difference between those big quantum computers that you see, on New York Times or Scientific American, where they take up an entire room like computers used to be in the 40s. You're telling me these are like ones that are room temperature that you can have them set up in a small sort of isolated location?
Yeah, so we still use some cryo detectors, but they're what we call an offline resource. So they're not on the computation part. I'm going to say these are not small devices. It's still a standard kind of data center rack. So you can imagine, the size of a cabinet.
Sure.
The actual chip themselves are really tiny.
So the image that you had for this event has the chip on a fingertip, right? That's the chip.
The fingertip, yeah.
State generation happens on that chip. All of the entanglement interference happens. Everything on that chip.
And then the rest of the structure around it is just isolating it and keeping it sort of from interfering with anything.
No, not even. The rest of it is just very standard control electronics. So a whole bunch of FPGAs in order to program the chip and do the readout. The standard, servers in order to put this thing on the cloud, all that usual stuff. But the really awesome thing is that we can cycle through these chips really quickly, meaning that in order to test one, because when we do a run of actually manufacturing these things, we don't replicate the same chip 100 times. We test a whole bunch of different approaches to try to minimize loss, increase the performance. And it means that the tests can happen at a much higher rate than they would if it was cryo-cooled. It takes about a day to pump down one of those dilution fridges, whereas here we could just swap them in and out. So basically the ability to develop faster, this manufacturability and the scalability is why we really believe that photonics will be the approach that gets you to that holy grail first. Some of the other approaches have some real bottlenecks in terms of how to get there.
Yeah, I mean that's exciting. That sounds like it's a pretty scalable and achievable method. And you're saying that a lot of this, the setups in the room are to get this information to the cloud as well. So you've got a version of this where people can actually go on and use your quantum computer.
Yeah, I think we have 13 more minutes before we take it down for the day. So if Paul's really brave, he can do a live demo. So we like I said, we've been online since September. We have facilities like the US DOE, Department of Energy, that have been leveraging these devices for their own research purposes. We work with a couple of banks in Canada as well as some other governmental organizations. So this has been up, and we're continuing to push the devices that we put up. Not only do we have these X series chips that you might have seen the video of and how they work, there's now additional architectures that we're putting up, which are kind of the building blocks for our fault-tolerant universal machine. So if people are really interested, in fact, we just had a Nature paper come out, I believe 2 weeks ago, that describes the whole cloud system and how that chip functions, and kind of gives you basic ideas on applications for it.
We can put a link to that in the YouTube description here. So if people want to check it out afterwards, we'll put a link to that paper in there to actually check it out.
Yeah, that'd be great. It's available on archive too, so you don't have to pay for anything, which is always nice.
Oh, fantastic.
And there are good summary articles as well. So if you don't want to read the actual paper, you can do that too. Someone like me can get the high level, the TLDR.
So, I mean, in terms of this cloud end, this is something that all the three of you are pretty much involved with the cloud end of this part, not in the actual production of the photonics or the quantum computing chips or the quantum computers. How do you find that the skills that I mean, clearly each of the three of you bring very different skills to this and do very different things with it. How do you feel that you add to it? I mean, Tim, you're a programmer there. You're probably working fairly regularly with that cloud end of stuff. You want to speak to that a little bit?
Yeah, sure. So I mean, at the end of the day, I kind of see it as software development is software development. The path that I've taken in my career has basically been built around the idea that to be a good software developer, you don't learn Python, you don't learn Java. You learn how to be a software development. You learn how to solve problems. The languages are just the tools to do that. So I go to work every day to solve problems. And that's basically what I'm doing, is solving the problems of making these quantum computers available to people. And what are the roadblocks that are standing in the way of that? And how do we tear them down and build the bridges to allow people to access these things?
Exciting. Paul?
What was the question again?
I say, how do you bring your specific skill set to this cloud project?
Oh, I don't know. I'm mostly a janitor these days around Xanadu, just kind of hanging out. But, no, honestly, like with the startup, like there's so much more work than there are people to do it, and I've actually found a lot of joy in being able to kind of jump around and do different things. So, was doing these ML AI products. We also do some ML and AI internally. So, for example, in the chip design. So actually designing the components of the chips to minimize loss. As Raf mentioned, like loss of photons is a big deal for us. So we need to minimize that, especially as we grow the system and scale. We have to couple things. You have to get loss down to, fidelity up to 99.999%. So we actually use AI to do that design to try to minimize the loss. So there's some internal machine learning going on, but then also just helping out with more and more. So there's so much software development to be done for the cloud. There's data, log data to be analyzed to see how we're performing. There's things like this, community outreach and engagement to be involved in. So I'm finding myself actually spread around multiple different things at the company these days, which I quite enjoy, because I can get bored easily doing one thing every day. So that's kind of where my skill set seems to fall these days.
Nice. And I mean, I guess to give you the opportunity, you keep trying to subtly mention this idea that there's much more work than you have people working there. So is Xanadu actively looking for more Guelph alumni or Guelph undergrads to hop the door and to take over?
It's not a requirement that you went to Guelph to work here. I should just say that. But yes, we're always hiring.
Exciting.
Yeah, we're going to be doubling within in size probably within the next year and a half. So we have a ton of positions open, from everything from developers, front-end developers. We're looking right now for a community person. So we have a couple of open source packages that we're trying to grow the developer community around, all the way down to engineers doing the electronic packaging and, photonic chip designers. Kind of across the board. Right now we have positions open.
Well, it's kind of an interesting thing too, even to get into. I don't know how much we need to talk about this, but the idea of joining a startup company and you're sort of like developing something from the ground up at that point. It's kind of an exciting thing to get involved with, to be on besides Tim, the rest of you have been on the ground floor of this, coming all the way up through. How do you feel about that? Is it the kind of thing where you feel more excited because you're actively involved in sort of all of these levels and you can see this thing grow?
Yeah, I mean, especially for me, like, having come from maybe the complete opposite of a startup, which is an 80,000 person company. I really like, so the term that we often use in places like that are silos. Things are very siloed, right? They're very, very delineated and separate, whereas that does not exist here. I mean, I could basically work anywhere in the company if I wanted to, if there was a place for me to contribute. I mean, I have done, detector. I've done hardware. I could go work in the hardware lab if I really wanted to and felt I could do something there. But like, there's no, there aren't the same kind of barriers, right? If you are excited about something and want to do it and can make a pitch that it's something you can contribute to, you can. No one's going to stop you. People will absolutely embrace that, which is really cool. I think it's something that for people that like exploring new things and trying a lot of different things, it's a great place for that.
Awesome.
I just wrote down that Paul volunteered to go work for the detector team. We actually are going to need somebody working there soon. So,
well, there we go.
I'm thrilled.
Again, in the words of Tim, it's all about solving problems. So just even through this live stream, we've got a solution for you right there. Well, we're getting about just a couple minutes out here of wrapping up. We got a few comments that are coming through and questions. So if I can get my mouse to work here, let's see what we've got coming down the pipe. Yeah, we got a Gabriel Gonzalez says that they're an undergrad and was looking to get into coding. I'd like some advice on what kind of languages I should be focusing on as building blocks. Tim, does this fall into your wheelhouse?
Sure. I'd say Python's probably a good place to start right now. It's sort of the hot thing in the sort of the scientific machine learning AI world. I honestly don't know why. It just is. Probably just because it is such an easy language to pick up and learn. So I'd say start there. If you really want to someday work for an 80,000 person company, you can learn Java.
Oh, we've got another question coming through here. This is from Mike Nelson. They're a PhD student at Guelph, also background in mathematics and electrical engineering, wondering what sort of outreach efforts you have for recruiting, interested in understanding and fitting my expa.
I mean, again, it's always a challenge with outreach for recruiting. We have our networks that we definitely recruit from. We post on all the usual websites, communities. That being said, we're a company of 70 people right now, so it's always challenging to devote the time to go looking for talent. Definitely what we'll do is maybe add the link to our website if you guys are interested to the careers page to take a look at what's there. But we also have a really good internship program that we just wrapped up for this year, but where we kind of put out a call to people that are interested in working with us for 4 months, fully paid, but just to find out whether this type of field is really for them. And we do this across the board, from software to algo to the hardware team, even our architecture team, which is like the fundamental quantum information theory team. So I'd say do that. Also for community outreach, I'd say we just wrapped up our developer conference. So we had 3,000 people participate in a hackathon called QHack. So if
I was actually just going to say this flows incredibly well into another question that's just popped up as well. I wanted to get a chance to talk about your QHack, your hackathon, and we got a third year who's interested in quantum computing, was wondering if you had any ideas as to projects which undergraduates could complete to get a better idea of what's involved in the field. I think, as far as I know, this falls directly into the QHack stuff. Is that something you guys like to chat about?
Yeah, so QHack had a focus not just on quantum computing, but specifically on quantum machine learning, which is another sort of hot field that's starting to pick up, and that Xanadu is sort of leading the way with. We have a quantum machine learning library that we've been developing for a number of years that's starting to really kind of pull ahead as one of the quantum machine learning libraries. It's open source, it's in Python. It's called Penny Lane, where our CEO is a big music fan, so our other open source software offering is called Strawberry Fields. Definitely, I would say, like, getting involved with quantum machine learning is a great place to get started with quantum, because you get to learn a lot of quantum computing concepts, but you also get to learn about machine learning, which is also really hot right now. And it's at that point where the field is so open that there's so much to do. Like, there's so many open projects and things that you can try and tackle. Our development team that works on Penny Lane is also fantastic at putting together documentation, tutorials, demos to get you started with quantum machine learning and Penny Lane. So, I mean, I personally, again, a little bit biased here, but I would say go check out Penny Lane. So pennylane.ai, check out that Python library and start on some of those demos and see if quantum machine learning is something that you're interested in. And there's huge scope there. Like, I mean, just starting with some of those demos should start to fire off ideas of potential projects that you could work on.
Yeah, just maybe to add a little bit on QHack. Penny Lane's not just for Xanadu. It's actually a completely platform agnostic library, so it can run on all publicly available quantum computers. So we had people from Google, IBM, AWS, all come and talk about quantum machine learning in the current state. And we ran that hackathon kind of focused around leveraging all these different tools using Penny Lane. So if you're interested in, learning about what Sandbox at Alphabet is doing with Flock, or AWS is doing with Bracket, or IBM is doing with their IBM Q experience, Penny Lane is like that perfect gateway drug, where even with no experience, you could just go and start running on hardware today.
I mean, the questions are coming in here fast and furiously. We got a BSc theoretical physics undergrad who wonders if I don't know how to say this. Knaime, Knime, would be a good option to learn machine learning for someone that does not know a lot about the subject.
I'm going to say, based on mine and Paul's faces, no. So maybe we're just too old, Paul, and but that's not a library that we came across. I'm assuming that's the library that they're asking about.
Yeah, I'm not sure. I haven't heard of it.
To tell you the truth, if you're interested in just regular machine learning, I would start from the ground up. sklearn is the Python package. And again, it's not the exciting stuff of deep learning or TensorFlow, any of that stuff. But what allows you to do is just get an understanding of like the basics, the roots. And then things like PyTorch and TensorFlow are really great at this very different approach to machine learning called differentiable programming, which just means that any piece of code is trainable. So if it's got a parameter that's free in it, you can train it using these things, but the complexity kind of goes through the roof. So if you're just getting started, go check out sklearn. Tons of Medium posts on your favorite linear regressions, boosted gradient trees, whatever you like, is all out there. Tons of information these days.
Yeah, it's always important, I think, to build your foundations first when you're starting, right? And if you're in the theoretical stuff as well, a good book, Elements of Statistical Learning is like kind of like the Bible for ML. Start there to get that really solid theoretical foundation, and then when you do get to the deep learning stuff, you'll just be crushing it.
Nice. Well, I mean, we're coming up close to wrapping up here. We have a closing question that we typically ask. Our reporter on the street, Mel, is under the weather this week, so she won't be joining us. So I'll be asking it. But I wanted to know before we got to that, is there anything in closing that we didn't touch on that anybody wanted to hit up in terms of a topic, or everybody's fairly comfortable? How do people, what's the best platform for people to follow Xanadu at and all of your work?
Probably Twitter.
Yeah.
Yeah, big into the Twitter. Yeah.
And check out the website, right? Xanadu.ai, and are there demos, or how do people access this cloud?
So yeah, we could definitely do that. One thing, there's a way to get yourself onto a waiting list. We're slowly onboarding more and more people. If there are people that are more broadly from an academic group, whether it be University of Guelph or somewhere, and there's a mass of you, definitely you can reach out directly to the sf@xanadu.ai email. That's in our documentation for Strawberry Fields as well. We'll throw up or share the links with the great Orbacks for Strawberry Fields and Penny Lane as well. So you could just get an idea of these open source packages. And there's a ton of information there. If you're interested in our research, everything goes on archive, everything goes on our website that we publish a ton. If you're interested in more just where we're at, what we're doing, what quantum Twitter, which is a real thing and a very funny subset of Twitter users, what's happening there, definitely follow us on Twitter. And then check out the YouTube page for the QHack videos from this year, which are really also a great introductory resource for people looking to get into at least quantum machine learning.
I saw that, and they just kind of all went up in the last couple of days, right?
Yeah, because they started disappearing from Twitch, which is where we hosted everything. So
Yeah.
There was a bit of a panic to get them up quickly. Yeah.
Exciting. Well, sorry. Go ahead.
No, I was just going to say they're not all actually up yet, but they should be all out by end of next week, I think.
Fantastic. Well, we'll close up with our classic ending question here, and I guess it'll be a question that I'll pose, and we'll go around. We'll let Tim get the last word in, so we'll go Paul, Raf, and Tim. And this is again our classic closing question here on the Guelph Physics live stream, which is again one that is sort of designed to inspire hope in our undergraduates who often are going into a stressful time with exams coming up. And it's this: what's been your most exciting day in the field? Whether it was research, doing experimentation, whatever. What's been the most exciting day of your career thus far?
Ooh, probably getting to write music for our QHack.
Oh, did you do all the sort of the 90s or late 80s?
That synthwave song that probably doesn't anyone saying because it plays all the time? Yeah, I wrote that. I made that with this stuff back here.
With that,
that was definitely my highlight of my time.
That's awesome.
Yeah, I mean, for me, it's just being completely out of my depth every day. There's something so fun about being thrown into something new, surrounded by incredibly smart people, and really the expectation is that you're just going to fail because there's no way to succeed. That's a really great place for me to work at. So I like that. From my academic career, like I mentioned, I used to work in Sunnybrook Hospital. And I remember the first day I got there, I had to be a subject for a neuro MRI scan. And I proceeded to fall asleep inside the MRI scanner. And when I woke up, all I could see out through the little mirror that you're looking through, that this giant tunnel, was a gurney with a pig on it. And I had no idea what was happening. I was so completely like discombobulated that I had like a full-on panic attack of like, where am I? What is happening? And it took like a good 30 seconds to calm back down. Like, it's your first day of work. This is normal. You're going to be fine. So yeah, that one will always live in my memory.
I'd say that for me, it's that one day where you write a piece of code and it works the first time through, and you spend the entire day trying to figure out what you did wrong. Why is it working? But it turns out, nope, you were actually just 100% successful for that one day in your life.
Amazing. Well, I want to thank the three of you for joining us here tonight. It's great to see you all again. And it's I think it's just a really exciting thing to get an opportunity to talk to three of our alumni who've gone on to, it's unique and exciting to go on and work at a startup, to happen to all be working together at a startup, but to be doing something that's so innovational and so new and has the potential to do so much exciting things in the future is a pretty great thing. So thank you so much for joining us. We really appreciate it. And I want to thank the viewers for joining us as well. Thank you so much for supporting the live stream. We're going to add all the links into the YouTube description that was mentioned in the chats here tonight. But we'll be coming back in a couple of weeks. So we've got an exciting one hopefully planned for just before exams. So tune in for that one. But in the meantime, thank you so much for joining us. I hope you enjoyed your evening. And we'll say goodbye here from Physics Hollywood at the University of Guelph. I'm the Great Orbax, and have a science-tastic day.